Hey guys, welcome back. Well, it's time to move on from the GT81. Had some good success with that. Enjoyed using the new mount for the first time, but now it's time to bring back the Explore Scientific 8102, a little bit heavier scope, more focal length, and I want to revisit some old targets, but first I want to try to deal with some stretched stars I have in the corners of my image. I've been using the Explore Scientific Field Flattener. It may be working fine and I just may be screwing it up, but I went ahead and bought the Hotec Field Flattener, which is intended for use with telescopes that have a focal ratio of anywhere from 5 to 8, and the Explore Scientific has a focal ratio of about 6.9 to 7. So I went ahead and bought this field flattener, and I thought I'd share with you my initial thoughts on it and take the time to revisit a fun topic from the old days, which is, so what is the effect of filter thickness on backfocus? Let's get started. So why am I moving to the Hotec Flattener? It could be just user error on my part with the Explore Scientific flattener that I have been using. This is it here. This is the side that's inserted toward the objective of the telescope. This is a 10 millimeter thick shoulder that sits at the back end, in my case, of a click lock that I hold it in place with. What I've been seeing and dealing with, and for the most part tolerating, in the corners of my images, I get these stretched stars, and I pretty much see this in all four corners. And even though I went through this experimental period where I swapped out different spacers and shims, and I thought I had the best field that I could get, I still wanted to try to get something better, and that's why I went off and bought the Hotec Field Flattener. Now, the Hotec Field Flattener, it's a larger item, both in terms of its projection into the bore. So this part is inserted into the telescope. This is the edge of my click lock here, and you would insert this in, turn the click lock to lock it in place, and then you would dial in, turn this knob here, and that will compress these rubber O-rings so that they expand out. It will help center the flattener within the bore of the holder here. Once it's installed, you have this amount, which is about 40 millimeters, that's sticking out, which exceeds the 10 millimeters I had here. We'll talk about the effect of that. And then finally I get back to my off-axis guider. I've got a spacer back behind here and a filter wheel, and then back to the camera. So this is the setup. This is what it looks like right here. And I just want to see if I can do a better job, darn it, of getting a flat field. Let's go over and take a look at a video of installing this flattener in my 8102. Over here on the Explore Scientific 8102, I'm going to make a few more changes. In addition to moving the imaging train from the GT81 over here, I'm going to remove the field flattener I have from Explore Scientific and replace it with this Hotec field flattener. And in order to do that, because this has a M42 thread and I'm looking for an M48 thread over here to interface with my off-axis guider, I'll be using one of these CWO converter rings that has an M42 thread on the inside and an M48 thread on the outside, and then that should allow me to make the connection. So the first thing I need to do is to turn the click lock and remove the field flattener from Explore Scientific, and then install the Hotec field flattener into the click lock, and we can tighten it down to hold it. And then we want to turn this, which expands the little O-rings that are inside the self-centering attachment. And as you turn this, it gets tighter and tighter as those O-rings expand within the barrel of this click lock. We can remove this and replace it with this ring here, which brings it up to an M48. And once we have an M48 here, we can bring the off-axis guider on and simply screw it onto here, and we'll be good to go. Well, how do you know if your backfocus is correct? If you have an image such as this, and this is a highly idealized image, but you find that you have stars that are elongated towards the center of the image in each of the four corners, then you have radially stretched stars, and what that is indicating is that your backfocus needs to be increased. In other words, the spacer that I currently have between my off-axis guider and my filter wheel needs to be wider, longer than it is right now. Right now I have a 10 millimeter spacer, so it would need to be somewhat longer. Now on the other hand, you may go too far, or if you look in your images, you may have a tangentially stretched stars where they are essentially tangential to a circle drawn in the center of your image. What this image aberration is telling you is that you need to reduce that spacer thickness or reduce the back focus. So there are some decent guides to help us fine-tune what the focus should look like. Now here's what I got when I went out and tested with my 10 millimeter spacer that's currently in my system. This is the Hotec Flattener, and the stars are arguably better than what I had been seeing. So maybe that's a step forward. But as I went around and looked at all corners of the image, and in this case I'm in the lower left corner, the stars are still a bit stretched here, and it's slightly worse in some of the other corners. This is what I'm seeing, which is clearly indicating to me that I've got radially stretched stars, and I need to increase the width of the spacer that I'm currently using. And now the only question is, how thick of a spacer do I need? Just to start off with a simple diagram here, we've got the centerline optical axis running down right down through the center of your telescope. We've got a ray of light coming in, being focused back here. So this is the focus point. And if you don't have any filters, then what you are aiming for is to satisfy the manufacturer's requirement of what their back focus is, usually 55 millimeters. This is your camera sensor. You want to have the back end of the field flattener 55 millimeters forward of that so that you have the correct back focus. But that's not the situation I have. I've got actual glass filters in between the field flattener and the camera sensor. So I've got something like this, and we'll assume the filter is made out of glass. It's got some thickness to it, and this ray of light will impinge on the forward end face of the filter here and come out somewhere, but it's not going to come out here. With a filter in place, the light is going to hit the forward face of the filter and then be refracted in, and then when it emerges on the other side of the glass, this line will become parallel to the line we had before. The problem is we end up with this offset here. Before we had a filter installed, this was the point where we were achieving focus on the camera sensor, and now with the effect of the filter, we are achieving focus back here. So let's just call these two distances distance A and distance B. And what we're after here is the effect of the filter on the focus point, on the actual focus point. And we'll call that C, and it's just B minus C. In order to figure out what the heck is going on up here in the glass, we need to take a look at Snell's law. Snell's law establishes the relationship between the index of refraction in air or a vacuum. The index of refraction is just a number. It's a non-dimensional number. It's very close. Air, it's slightly higher than in a vacuum, but not much. So for all intents and purposes, we're just going to call this the index of refraction times the sine of this angle here, and that's equal to the index of refraction of glass times the corresponding angle on the other side. For our purposes, we can take advantage of this small angle assumption, and that means we just get rid of the sine, and we can just have the index of refraction in air times the theta, the angle of incidence here, is equal to, for our purposes, the index of refraction in glass times the corresponding angle in glass back here. And if we plug in some numbers with n equal to 1 in air or a vacuum, and for glass the index of refraction is about 1.5, then the angle here is about 2/3 of the angle in air. So we'll just make use of the triangle here and calculate this side, divide by the tangent of theta, but hey, we don't have to deal with the tangent. We just said angles were small, so that becomes theta. And if you take a moment to look at the geometry here, you can see that you take this height from here, where this dashed line crosses the back face of the filter, minus this distance here, t times theta, and divide it by theta. That becomes the distance A back behind the filter, where the focus point would be if we had no filter. If this were air, this is where we would be focusing, but it's glass. And if we take advantage of, again, a larger triangle now, because that point is, the red line is impinging a little bit higher up here, now we have h minus t times 2/3 theta, again 2/3 coming from this ratio of these indices of refraction, and we get b, and then simply subtract those, and we get C is equal to T minus 2/3 of T, which is T over 3, and you've probably heard that before. In other words, the effect of a filter is 1/3 the thickness of the filter glass. So there's a reason for that. It's important that we understand that this is a kind of a constant here. It didn't matter what this angle was. It didn't matter where on this filter this ray of light impinged on the filter. It's just T over 3. Now we can make use of this information to determine the actual spacer we need to flatten the field and satisfy the field flattener manufacturer's backfocus objective. Here's our equation, and this is the important part here. We have the flattener backfocus that comes from the manufacturer, and then the filter effect is added to this side of the equation. Oftentimes you'll see someone respond, well, you add the effect of the filter. Well, that is true, but are you adding it to this side of the equation, or are you adding it to the spacer side of the equation? The important thing here is that we are adding this filter effect to the field flattener manufacturer's backfocus requirement. Hotec tells me that their backfocus is 55 millimeters. The ZWO filters I'm using are about 1.9 millimeters thick, and then we take 1/3 of that per this equation over here, and that gives me about 0.6 millimeters. And so my actual backfocus that I'm targeting here is actually 55.6 millimeters, not the 55 millimeters that is provided by Hotec. On the other side of the equation, I've got my ZWO off-axis guider at 16.5 millimeters. I'm trying to find out what the spacer length is. I've got a filter wheel from the forward face of the filter back to the back face of the filter. That's 20 millimeters. So it doesn't matter that we've included the effect of the filter inside the filter wheel, but that's a different effect than the optical length of the filter itself. The effect of the filter glass is this refraction effect going on through the glass. That's what we're accounting for, and that's what ends up over here. The thickness of the filter wheel, 20 millimeters in my case for the ZWO filter wheel, is added in on this side. And then finally for my ASI 1600, the sensor is set back 6.5 millimeters from the forward face of the camera. For my system, your mileage may vary, but for my system, I need a spacer thickness of 12.6 millimeters. My first image with a 10 millimeter spacer told me that that 10 millimeter spacer wasn't long enough, that I had to increase the spacer thickness, and this calculation is showing that I need to increase the spacer thickness, and so that's what I need to do next. Now it's time to try to deal with the field flatness, and so I need to adjust the spacing, and for that it's that spacer just to the right of the off-axis guider between the filter wheel and the off-axis guider. That's currently at 10 millimeters, which leaves me a bit short on the overall back focus. Our target is about 12.5 millimeters. This is the Celestron 6 millimeter spacer. This is the 5 millimeter blue fireball spacer, M42 threads. This is the 6 millimeter spacer. So in theory, I can put these two together and get 12 millimeters. And if I measure that, I indeed come up with 12 millimeters. Do I want to put one of these spacers that I ordered in there? So ideally, I would put in about a 0.5 millimeter spacer. I don't know if I want to trust the numbers that much, and I may do something less than 0.5 millimeter. So here are the 0.6 approximately spacers. These are about 0.8. These are 1 millimeter. And as I said, this is about 0.4. So I think if I want to get close without going too far over, I'm going to put one of these 0.4 spacers in the stack up here along with this combined 12 millimeter spacer. So that gives me about 12.4, looking for about 12.6. All right, so now I've got approximately a 12.4 millimeter spacer between the off-axis guider and the filter wheel, having replaced a 10 millimeter spacer and a shim that was in there from the ZWO package. The current spacing is theoretically correct. All right, so the next step is to wait for the slides to clear and do some imaging tests to see how this did with flattening the field. Stand by. So after reassembling the setup with the 12 point, in my case, 4 millimeters that I'm trying out, I had to go out and obviously refocus the camera for this roughly 2.4 millimeter shift in the focus point. And then I had to play around with the guide camera of my off-axis guider to compensate for that 2.4 millimeters of shift in the back between the center of the off-axis guider and the imaging sensor. I have to also capture that distance shift in the moving the guide camera out by 2.4 millimeters as well. And so I did that. Now I want to compare images I took back in January of this year, where I was imaging the Jellyfish Nebula with the ED-102, and images I just acquired trying to finish up collecting data on this target, but now with a hopefully a lot better flat field than I had before. Let's zoom into the corner, and this is obviously in the lower right hand corner of the image. This is the kind of image stretch that I was getting. You can see there are kind of teardrop shaped stars going again radially towards the center of the image, whereas here I'm getting very nice stars in the back, maybe a little bit of stretch to them. I can see maybe a little more stretch in some other corners. I'm quite pleased with the effect of the Hotech Flattener, and who knows, maybe in the next imaging session I may go in and replace that 0.4 millimeter shim that I put in with the 0.6 millimeter shim, just to bring the back focus to the theoretical requirement of 12.6 millimeters and see if that does anything. I'm actually quite pleased with these results. Okay, so what are our comments and conclusions about the Hotech Flattener? Well, first of all, I'm trying the Flattener out, and it's a Flattener that applies to a range of telescopes from an f5 up to an f8. My ED-107 is an f7, so it's right in the middle of the range there. I'm trying it because I just haven't been happy with the Flattener that I have been using. It could very well be user error on my part as why I wasn't getting as flat of a field as I would like. Hotech claims that the self-centering adapter reduces vibration, and I think this is just a go-to move for engineers. When they see that rubber is involved in some sort of a system, they assume it eliminates vibration. The part they're forgetting is that the presence of an elastomeric substance also provides relative movement, which is actually critical in reducing vibration. If we had significant vibration reduction here, we would also have significant relative movement of the Flattener relative to the telescope, which is the last thing we want. We don't want sensor tilt. We don't want flexure. We want good optical system that will flatten the field and stay centered. A stiff system, not a vibration isolation system. Those two things don't go together. Buy the Hotech Flattener because its optics are awesome and it seems to work quite well. Maybe the O-rings do provide a self-centering component to the design, but the stiffness of the rubber, thankfully, is so stiff that it cannot possibly reduce vibration, and therefore does not, apparently, at least to the extent that I can tell, introduce sensor tilt or flexure into the performance of the overall system. The exposed part of the Hotech is 40 millimeters long compared to, say, the 10 millimeters of the other Flattener that I have. This is something you need to think about. That 40 millimeters is going to push your camera sensor farther back, and you're going to have to compensate for that by bringing your focuser in. And in my original case, when I first installed it, I didn't have enough travel in the focuser to do that, so I had to remove a tube spacer in order to achieve that additional inward motion of the camera sensor. We showed how we need to add 1/3 of the filter thickness to the manufacturer's back focus requirement in order to properly account for the focused shift point that moves farther back when you introduce glass into the light path. For me, the back focus is 55.6, 55 from the field flattener and 0.6 from 1/3 the thickness of the filters that I'm using, instead of the 55 millimeter required with no filter. We also looked at the image characteristics that give us a hint as to whether or not we need more or less back focus. If the stars are stretched along a radial line pointing at the center of the image, then you need to increase your back focus. On the other hand, if the stars are stretched more in a tangential direction, that is tangential to a circle with a center at the center of your image, then you need to reduce the back focus. I have changed the spacer between my off-axis guider and my imaging sensor, which means I have pushed my imaging sensor 2.4 to 2.6 millimeters farther back. That also means with an off-axis guider that I've got to move the guide sensor out 2.4 to 2.6 millimeters in order to maintain focus. The second thing is I use my whole camera rig from the off-axis guider back to the camera and just move that from one telescope to the other. When I put this on the GT81 next time, I'm going to have to go back and readjust the adjustable focal reducer field flattener on the William Optics GT81 because now I've moved my imaging sensor 2.4 to 2.6 millimeters further back, and so I need to compensate for that in the adjustment in the William Optics focal reducer and field flattener. So in the end, I'm very impressed with the Hotec field flattener. It certainly does what it is advertised to do from an optical standpoint. If you're looking for a field flattener and you have a refractor in the f5 to f8 range, be sure and consider the Hotec flattener because I think it'll do a good job for you. Okay guys, well that's all I've got for us today. Thanks for checking in, and I'll talk to you later. See ya.